Okay, we left off talking about the synthesis of water from hydrogen and oxygen and how that's an exothermic reaction. And we saw the thermochemical equation that listed the delta H at the end of it. This is another way of showing a thermochemical equation. You just kind of need to get used to seeing these. It's just a little graph showing the increase in enthalpy, comparing the products to the reactants. And so you'll have to be able to create these. So a lot of times people look at this and they're like, okay, so do the reactants always go on top? No, they don't. It depends on whether the reaction is exothermic with a negative delta H or endothermic with a positive delta H. So this just requires you to think about what that negative sign means. Okay, that negative sign just simply means energy was released when the reactants turned into products. Therefore, since energy was released, that means our products must have less energy than our reactants did. So that's why the reactants go on top. And you draw the arrow pointing towards the products. You always do that. And then put the products on the bottom because they have less energy. They have less enthalpy because this much was lost in the course of the reaction. On the flip side, if we had an endothermic reaction with a positive delta H, we would put the products on top instead, because if it's endothermic and it absorbs heat, then, or absorbs energy, that means our products end up with more energy. So they would go on top. And then the arrow, just like in a chemical reaction, is always pointing at the products. So if it's endothermic, you would just set it up the exact opposite of this. All right, so things to remember. Extensive properties versus intensive properties. I have a hard time remembering these myself. I always get them flipped around. Extensive properties do depend on the amount of substance present. A simpler example besides enthalpy would be mass. Obviously, the mass of a substance depends on the amount of the substance present. Mass, volume, and enthalpy, energy, obviously that depends on the amount of substance present as well. On the flip side, intensive properties are not related to the amount. So for example, if I say the temperature of water is whatever, 25 degrees Celsius, it doesn't matter whether I'm talking about a little test tube full of water or a whole bucket full of water or an ocean full of water. Okay, if I say it's this temperature, that's what the temperature is. It's not going to matter how big or small the sample is. So intensive properties do not relate to the amount of matter present. Color's another one. Like color's a simple one. If somebody's wearing a pink shirt, it doesn't matter if we're just looking at the sleeve or the whole shirt. Okay. All right. Going back to that density. Would density be extensive or intensive? Okay, that's a tricky one for people. Density is mass divided by volume. Well, mass is extensive and volume's extensive. So would density be? No, because the extensiveness kind of cancels out. Okay, you end up, like if you're talking about the density of water, we all know the density of water is 1. There's 1 gram per every 1 milliliter. That's true whether you're talking about a little bit of water or a whole lot of water. So density, while it's based on 2 extensive properties, density itself is an intensive property. It does not relate to the amount. I think that one pops up in your homework. All right, so enthalpy is extensive, which makes sense. You know, the more butane you burn, the more energy is going to be released, the more enthalpy there's going to be. So therefore, the magnitude of the enthalpy is directly proportional to the amount of reactant consumed. We said if, you had a balanced equation, it's that enthalpy is related to the coefficients, the amount of moles. So for example, if 1 mole of methane is burned in oxygen to produce CO2 and water, 809 kilojoules of heat are released. So that would be negative 890. What if we burn 2 moles instead? Well, twice as much would be released. Okay. Notice I don't have a negative written in front of these. It's implied though, because I'm saying heat is released. Okay, so if I were to ask you to write what the delta H is, you would need to just realize, oh, because heat's being released, that would be a negative 890 or a negative 1780. So a lot of times in the homework, it's just going to list an enthalpy, and it'll say heat's being released or absorbed. You have to figure out the sign yourself. Okay, so the delta H depends on the direction of the reaction. Okay, we talked about, on the last slide, let's go back to it. 890 kilojoules are released when we burn methane. Well, can you take that carbon dioxide and water and turn it back into methane? Yes, you can. Just to do that, you're not going to release energy. You've got to put all that energy back in. Okay, so the opposite reaction would still have the same value, but the sign would change. That's something that it makes sense, in order to get the reverse reaction to happen, you would have to put in all the energy that is released during the forward reaction. But a lot of times people will say, like when they're talking about fossil fuels and whatnot, and they're like, well, why don't we just take the carbon dioxide and water out of our exhaust and turn it back into gasoline? Okay, that is chemically possible, but you would have to put all that energy that was released back into it. So it wouldn't be cost effective, I guess, in terms of energy to pull that off. Okay, so the sign of the delta H just depends on the direction of the reaction. Okay, the enthalpy change for a reaction is going to be equal in magnitude for the reverse reaction. It's just going to have the opposite sign. So you can flip a reaction around backwards and just change the sign. That's totally legal. That's something you're going to have to do in your mathematical calculations. So for example, here's our methane burn-in. Delta H is negative 890, meaning that much energy is released. If we want to go the other way, if we want to turn that CO2 and water into methane and oxygen, we can do that. We just have to add 890 kilojoules. Extra animation for no reason. Okay, so thermochemical equations. We can use those stoichiometric coefficients, right, the numbers we use to balance it. We use those to refer to the number of moles of a substance. That's not a new thing for us. So right here, this is just melting an ice cube, okay? Turning solid water, ice, into liquid water. That takes 6 kilojoules of energy, has to be added, so there's a positive. We don't write the positive, you don't have to write the positive, but it's implied that it's positive, to melt 1 mole of water. If you want to go the other way, if you want to freeze your water, you want to take liquid water and turn it into an ice cube, you can reverse that reaction up there. You just have to change the sign. It's still 6.01 kilojoules. It's just going to be negative because this time we have to take energy away instead of add it. Okay, so states matter in thermochemical equations. You'll see what I mean by that in later problems, but especially substances like water that can easily exist in all 3 states. We see water as solid, liquids, and gases all the time. You don't see other substances in all 3 states very often, like gold, you don't see melted gold every day, but water, you do, and you have to pay attention to that in the chemical equation. So when you write them out, you got to make sure to include the state. Okay, if you multiply both sides of the equation by a factor of n, like say you double all the coefficients, that's legal. You just have to make sure to double the delta H too. So if we wanted to know how much energy it would take to melt 2 moles of ice cubes, then we would just multiply our kilojoules by 2, and so it would take about 12 kilojoules. All right, so as I said, enthalpy does depend on state, okay? Gaseous water, steam, has a lot more energy. It's a gas. Gases are the highest energy particles, and then solid would be the lowest with liquid in the middle. So to turn a gas into a liquid, okay, that liquid has less energy than a gas does. You would have to remove some energy, okay? So to cool steam down into a liquid, you would have to remove 88 kilojoules. So when you're doing thermochemistry problems, you can't treat liquid water and gaseous water the same because they have a different energy value, obviously. Okay, so the physical states of the reactants and products must be specified in thermochemical equations. Because solid going to liquid water, that's 6 joules, but liquid going to gas, that's much more energy is needed, okay? It doesn't take nearly as much energy to melt an ice cube as it does to boil a mole of water. Okay, so several times more energy is needed. That's because liquid molecules have a little bit more energy than solid, but the gaseous ones that are flying around super fast all over the place, those have the most energy by far. So this is why it's so important to pay attention to the state, because it does definitely make a difference. Okay, so let's do a problem with this, a stoic problem with this. How much heat is evolved when 266 grams of white phosphorus burns in air? Okay, here's our balanced equation. For every 1 mole of P4, we need 5 moles of oxygen, and we'll produce 1 mole of P4O10. That's not supposed to be X'd out. That's supposed to be a plus sign. Pretend this delta H is just part of the chemical equation. There's a 1 to 5 to 1 to 3,000 kilojoule ratio here. So for every mole of product that we make, we're going to release this much energy. So we're just going to do a stoic problem. We're given 266 grams of white phosphorus, of P4. So grams, as always, are useless, so we have to convert them to moles using the molar mass. And then, just like you can convert from moles of any substance to any other substance in the equation, you can convert from moles of any of these things directly to kilojoules, if you know the delta H. So my next conversion factor, I'm going to convert moles of P4 to kilojoules. And according to this thermochemical equation, for every 1 mole of P4, there's 3,000 kilojoules released. Okay, so that's a new style of conversion factor. Probably. I assume you haven't done this before. All right, so do the math. And so if we burn 266 grams of white phosphorus, it would release 6,470 kilojoules. Don't forget to write that negative. All right, so here's an example from the book. How much heat is released when 4.5 grams of methane is burned in a constant pressure system? Get used to seeing that constant pressure thing. It doesn't mean you have to do anything extra. In fact, it simplifies things. It's saying because it's a constant pressure system, no work was done. So all of our enthalpy is coming just from heat, just from Q. All right, so here's our thermochemical equation. For every mole of methane that's burned, we're going to release this much energy. So once again, take your grams of methane, convert it to moles, and then there's a 1 methane, an invisible 1 written here, to every 890 kilojoules of energy released. Ta-da! Don't forget to write the sign. Okay, a lot of times people forget to include that negative there. All right, I'm going to stop at that because calorimetry is a whole nother ball of wax that I cannot cover in 2.5 minutes.